So I'm Yantai from Yale, and today I would like to talk about our new work on using tools from recommender systems to help mechanism design. And this is joint work with Daskalakis from MIT. Okay, so the question I would like to talk about is similar to what have been discussed a lot in this session. That is, I want to design a revenue optimal mechanism to auction multiple items to multiple bidders. And I will be in the setting where the bidders have private types, their utilities are quasi-linear. And I think for this audience, I don't need to explain that if the seller has no information about the buyer's values and types, this is not even a meaningful optimization problem. So the classical theory makes the following assumption, that is, the seller knows a distribution from which these types are drawn from. And under this assumption, Myerson showed that there's a very simple and elegant characterization of the optimal mechanism if we're only selling one item. And if we are selling multiple items, the problem is much more complicated. And we just heard a great talk about this. And so there's no simple characterization of the optimal mechanism, but there has been a lot of recent progress on various fronts. But for today's talk, I would like to re-examine the assumption, the Bayesian assumption, and I want to understand where do we actually get this prior F. And a common answer you will get about this question is that you can get F by doing market research or maybe observation of bidder behavior in selling the same kind of items in some prior auctions. Depending on those auctions were truthful or not, you may also need to do some econometric analysis to revert the bids into values. But in any case, we still don't have, we don't know F. Our best bet might be that we know a approximate distribution F hat of the true distribution F. Okay, so we need to use an approximate distribution F hat to design a mechanism that works well for F. In today's talk, I would actually like to make one more assumption. That is, this approximate distribution F hat actually has some nice structure. And I would like to argue that this is a realistic assumption. That is, if you are really in the case where F is high dimension, don't think about F as 2-dimension or 5-dimension. Maybe F is 100-dimension or 1,000-dimension. Okay, so in those cases, these high-dimensional distributions are very hard to learn. Okay, and one effective way to learn these distributions is actually try to approximate them using more structured models. And there are a lot of tools from statistics and machine learning that allows you to do such approximation. And there are many different structured models that allows you to, they're out there for you to choose from. For example, graphical models or topic models. So that's one reason why I want to think about the F hat actually has some structure. And I also would like to argue that maybe even if you really know F, there's some good reason for you to replace it with a approximate distribution F hat that has more structure. So the reason is that if you want to just design a good mechanism for a arbitrary high dimensional distribution F, that's usually quite challenging in terms of computation, representation, communication, a lot of things. But if you have an F hat that has more structure, perhaps you can use the structure to improve the mechanism design. All right, so the goal of today's talk is to show you how you can design mechanism for the true distribution F, while you only know some approximate version of it, the F hat. And also I'm going to assume F hat has some structure and show you how to use the structure to improve some aspects of mechanism design. And the F hat I would like to focus on is known as the topic models. So topic models are actually quite successful models for capturing agents' preferences. So here, so let me first, explain what is a topic model. So in topic model, so here's the basic premise. Suppose you want to generate a high dimensional vector T, say in Rm, and here let's use the example I was showing up here that I want to maybe auction seats in all New York City restaurants to maximize revenue. So M here will be the number of restaurants. So, and M could easily be, a few thousands. And so now every bidder has a m-dimensional type vector. And the basic premise here is that you can generate T, the m-dimensional vector, using the following very simple stochastic process. What you do is you first sample a mixture over k archetypes. Okay, think about our archetype correspond to one particular full connoisseur. And then you output a n-dimensional vector by combining the preferences of these archetypes, of course, in a way that depends on the mixture you sample in the first step. Okay, and many models are based on this premise. For example, the non-negative matrix factorization, latent Dirichlet allocation models. These are all successful models people use in practice. Okay, so let me be a bit more formal here and tell you exactly what is the model that I want to talk about. So here on the left-hand side, I have the true bidder types. So every row is a bidder's preference over the M restaurants, okay? And each row is sampled independently from the true distribution F sub I, all right? So I don't know the true distribution. What I know is the right-hand side, which is a topic model. So let me explain what is this topic model here. So the orange matrix represents the archetype's preferences over the restaurants, okay? And every row here is a particular archetype preference over the restaurants. And I'm gonna assume this orange matrix is known, okay, and doesn't change. And here you have this blue tall matrix. What is this matrix? So every row of this blue matrix is a particular bidder's mixture over the archetypes, okay? And I'm going to assume every row of this blue matrix is sampled independently from some different distribution Fi hat, okay? And I'm going to multiply the blue matrix with the orange matrix. I will get a matrix that's also m by m, which is of the same size as the left-hand side, okay? So the right-hand side also is a distribution over the bidder's types, okay? But it's not the true distribution. What I'm going to assume is this right-hand side distribution, the topic model, is a good approximation of the true one, okay? And I would like to design a mechanism when I only know the right-hand side topic model, but not the left-hand side true distributions. That will work well for the true distribution F. Okay, so that is the model. And the first challenge, I already mentioned it, that is I only know approximate distribution, and I want to use it to design a good mechanism, even for the true distribution. Okay. But here there's a different challenge that we're facing. So if you go back to the particular example I was giving you in the previous slide, that I want to auction, seats in restaurants in New York City. So I'm really dealing with a problem where M is huge. M is in several thousands. And it's just impractical to use a direct revelation mechanism. You cannot ask bidders to communicate their n-dimensional type. So the question is whether we can use this F hat, the particular topic model here, to simplify maybe the communication, okay? And the natural idea is maybe you can just ask the bidders to report their mixture over the archetypes, right? So since their types really only depend on this k-dimensional vector, why don't you ask them to report the k-dimensional vector? The problem here is that this right-hand side model, the topic model, is just a construct. It's a machine learning model that's probably sitting in the data center, But the bidders don't really know what's their mixture over the archetypes. They know their n-dimensional types, but not the topic model. Topic model is just something we made up so that we can actually solve this mechanism design problem. Okay, so you cannot directly ask them about their archetypes. All right, so these are the two challenges this particular model poses. And what I would like to do in the next few minutes is to give you a sketch on how we can address these two challenges in this topic model. All right. Okay, so for the first challenge, I'm going to use a robustification procedure that was developed in earlier work that works in quite general settings, and it will be applicable here as well. And then we need to do something extra to address the second challenge. Okay, so what's the robustification procedure? So it works in a very general setting. So you have multiple bidders, and you allow the bidders to have multidimensional types, quasi-linear utilities, and there's some extra technical assumptions which are not super important here. And in this setting, the seller only knows a proxy distribution f hat, and also was given the promise that the true distribution f is not far away from this proxy distribution, meaning the true distribution is within the it lies in the epsilon ball around the proxy distribution. And the particular metric we'll pick here is the Prokhorov distance, and its definition is here. But I think for you to understand the talk, the particular definition is not super important at this moment. You just need to, just keep in mind this is a very liberal metric. It's actually more liberal than most of the familiar metrics like total variation distance, Wasserstein distance, and so on and so forth. All right. Okay, so the seller only knows the proxy distribution, and the true distribution is not far away from it, but doesn't know exactly where the true distribution is. And what we achieve in this robustification procedure is we show that you can robustify any mechanism in this model. What do I mean by that? Suppose you have a m hat that's designed for f hat. Okay, by that I mean m hat is a big and IR mechanism and probably has good revenue with respect to f hat. Now there is a generic robustification procedure that's oblivious to f, and you can apply it to m hat to get a robust mechanism m sub r, such that it gives you the following guarantee. Okay, so it guarantees that for all f in the epsilon ball, the robustified mechanism is approximately IC, exactly IR, and its revenue under the true distribution is only a little worse than what m hat will get under f hat. Okay. And so this, it might seem a little weird that the right-hand side I put the revenue of m hat under f hat here. But if you think about it for a minute or two, you will realize this is actually quite strong guarantee. It implies that, for example, the optimal revenue under f and f hat are close. So if m hat is approximately optimal for f hat, the robustified version, the m sub r, is approximately optimal for the true distribution f. Okay, so it's pretty strong guarantee. And we're going to apply it to our topic model. And so this gives us a very modular approach that allows us to learn mechanism from data. Okay. And it has three components. So the first component is you try to learn a topic model f hat that approximates the true distribution f in some Prokhorov distance. Note that this is a completely learning task. You don't need to know what's the downstream application of f hat. Okay, just do the best to learn the topic model. Okay, and then in step 2, now we already can use topic model to simplify the mechanism design. So just design a mechanism m hat for the topic model f hat. The important thing here is that f hat actually is a k-dimensional distribution rather than an m-dimensional distribution. Okay, and for topic model to be interesting, of course, we should be in the case where k is far less than m. So that supposedly would make the mechanism design problem a lot easier. Okay, of course, there's a tricky issue here that the mechanism you design using f hat will ask bidders to report mixture over archetypes rather than their m-dimensional types. So we need to make this m hat somehow be able to take directly interact with bidders with m-dimensional types. Okay, so that's what we did in the last step. So in the last step, we robustify m hat into some mechanism m sub r that will give you good revenue on the true distribution f. Okay, and also we actually make m sub r an indirect mechanism where we ask the bidder some sparse queries. For example, the queries will be like, how much do you like this particular restaurant? And by asking a small number of these sparse queries, we actually can sort of learn their mixture of the archetypes and then use m hat. Okay. Right, and I say the number of queries we ask here scales quite mildly in the number of archetypes and is independent of n. Okay, so this allows you to actually save the communication. The communication now no longer depends on n, only depends on k. Okay, sorry, how much time do I have? Yes. Okay.
Let's say 2-3 minutes.
Okay, thank you. Thank you. All right, so let me actually make this a bit more concrete for you, and I'll wrap up. Okay, so I'm saying there is a modular approach that allows you to learn mechanism from data using topic models. So the first step is just learn a topic model to approximate the distribution. Okay, so that's, I call this the machine learning component. And then the second component is just design a mechanism that deals with the f hat, the approximate distribution, the topic model. And that's the second component. And then in the last component, here's what the mechanism will look like. So you have a query protocol that interacts with the bidders. The bidders all have m-dimensional types, so they don't know what's their k-dimensional representation. Okay, but what the query protocol does is to say that if the type of the bidder actually lies close to the manifold, so in this case, meaning that if there is some z, a k-dimensional vector zi, such that ti is not far away from zi times a is the preference matrix of the archetypes, then the query protocol, by asking a few number of queries to the bidder, would output a z tilde that is not far away from the true z. Okay. Of course, the query protocol does not know z, okay? But we managed to show that if A has enough diversity, you can actually achieve such guarantee. So the query protocol asks a few queries and will learn some z tilde that's not far away from a z, okay? And then you submit these z tildes, basically the learned latent types of the bidders, to a mechanism m tilde, not the m hat that you design in step 2, some different mechanism. And this different mechanism is just a robustified version of m hat in the latent space. So why do you need to do the robustification? Here's the reason. Because when you learn the z tilde, you actually are getting some distribution. That's not f hat, okay? So you're getting some distribution, I'm calling the f tilde. And what you can prove is that if f and f hat are close in Prokhorov distance, okay, I'm saying f hat because, but really you need to multiply a to a sample from f hat. But if your topic model and the true distribution are close in Prokhorov distance, you can actually prove that these f tilde and f hat will actually be also close in proper distance. And you can apply the Robustification procedure to get M tilde so that it works well for this Z tilde you like. All right, so that's the what the mechanism will look like. And let me wrap up. So we provide a new model that allows you to combine mechanism design with topic model, a very popular statistical model for capturing preferences in recommender systems. And we also show that not only you can use this topic model to get a mechanism that works well for the true distribution, and also we show that you can use topic model to improve communication complexity. So I think there are many opportunities here in mechanism design with high dimensional structure distributions. So we look at one particular structure distribution, the topic model, and we try to improve one particular aspect of mechanism design, that's communication. But there are many different structure distributions you can think of, like Markov random fields, Bayesian networks, and you can try to say the types are coming from these structure models and try to improve different aspects of mechanism design, for example, computation, representation, or maybe approximation ratios. Okay, and that's all. And let me stop here.
Thanks. Is it incentive compatible for the agents to correctly answer the questions about their preferences, or is there a way for them to get better prices if they lie?
Yeah, that's a great question. So the IC guarantee here is similar to epsilon big, but a little weaker. So what we can guarantee is for a particular bidder, for the majority of their types, they can deviate and get, but not getting more than epsilon. But for a small proportion of their types, they might be able to deviate and get more than epsilon. So that's the kind of solution concept we have here. But that's kind of unavoidable because there's a lot of error happening in this approximation going between the distributions. So that's the best we can get at this moment.
Do you have any intuition for why the agents want to report truthfully?
I mean, they might report they don't. Okay, right. So if they report truthfully, they will get something that's close to this ZI I was showing you earlier. So let me actually go to that slide. Okay. Yeah, so saying, right, so for most of the time, the bidder's type will be close to some ZI times A, okay? So if that's the case, if they report truthfully, the mechanism will figure out a ZI tilde that's not far away from ZI, okay? And the mechanism we're running is truthful for ZI, or approximately truthful for ZI. So that's the reason they don't want to lie and get something that's very far away from ZI. They might as well just report truthfully and get a ZI tilde that's not far away from ZI. So that's why you get approximate incentive compatibility. Does that answer your question?
Yeah, I think that answers it.
All right, let's thank the speaker again. Sorry for being a little over time.
Jan, can you stay for a second so I can ask you questions?
Sure. I'm assuming about the talk.
Thanks. Is it crucial that for the topic models, they all have, for each bidder, you have the same matrix A? Or would it work just as well if you had like a different topic model for every bidder and they each had a different, in addition to that, they had a different mixture?
Yeah, I think it's fine if you have A sub I rather than just A. And yeah, like it's just, I think the same proof will work out. It's just like now, like for every guy, the query protocol will need to use their own AI rather than just A. But I think everything will work out.
That makes sense. And then the second one is the query protocol is completely modular from, oh, thanks. The query protocol is completely modular, so it's like separately for each bidder, you just, or it doesn't even need to be, you have this query protocol that has nothing to do with any of the other bidders, has nothing to do with the fact that you're using this mechanism. It's just you're trying to learn what their valuation vector is, and that's just a completely modular problem.
Yes, yes.
And so then in the end, so what's happening in the end is really there's this distribution d tilde, or this real distribution d tilde, which is like you're going to query the bidders, take the responses of their queries, and like that's the distribution of what you see. And then you build this, and then you just have like all these different steps of needing to robustify it because this is through several. Okay, cool. That's thank you.
Yes. So there are like 3 different distribution play arounds. So I have to robustify basically a few different things. But right. Yeah, but the query protocol doesn't need to know what the mechanism is doing. It's just a complete separate step.
Hi, Yang. I was wondering what kind of guarantee you have in terms of recovering the underlying distribution f. Do you need to say recover the latent variable z as well, or you only need to? Yeah,
I see. So you're asking me whether I can still get the result without recovering the z. Is that what you're asking?
Usually in statistics, recovering the latent variable, identify the latent variable itself is pretty hard. You need some separation or separation condition, something like that.
Yes, that's what I was saying when you want the A to be diverse enough. So that's the exactly type of the condition we need. And so that's a good question. So basically the issue is that if you don't recover the Z, you would get this F tilde distribution that could be very far away from the F hat, could be very far away from the topic model. So now the robustification part fails. So it's no longer this kind of modular approach we can apply here. But it's just maybe because the approach we're taking. But you might do a different approach. Maybe it's fine.
So what kind of norm guarantee do you have for recovering the latent variable? You want say what if I can give you L2 norm guarantee? Is it good enough?
L2 norm guarantee for what?
For estimating Z.
No, you need something stronger. I think we need actually L infinity.
Oh, okay. That's interesting. I'll read your paper to see how you did this. So you're the instant.
Yeah, I mean, like
we can get say L2.
I mean, okay, all right, sorry, like L2 in the k dimensional space.
Yeah, in k dimensional space.
Yeah, I mean, actually, that wouldn't we actually don't care that much in the k dimensional space because in the k dimensional space, I mean, I'll pay another factor k or something. That doesn't matter. I think what we care about is I don't want something that's like L2 in the n dimensional space. Because I think I need something that's L infinity n dimensional space, and that I'm going to pay the n, which is a lot. But I don't care about paying things in the k dimensional space. I think if you get something L2 in the k dimensional space, it's fine too. Right.
So what if say when estimating f, so suppose I give you the total variation distance guarantee, is it good enough for you? Or you need something stronger?
I think Prokhorov is just easy to work with because there are a lot of steps that you have errors. For TV, I would need to check, but like TV, you're not allowed to basically shift the support and so on, right? So like I think some of the steps maybe you would shift the support, and so that could just screw up the whole guarantee.
Okay.
Yeah.
Okay.
Right.
Thank you. Thank you.
Okay. Cool.
Yes. Thank you very much. That was a lovely talk.
Thank you.
You have a good day now.
Yeah, you too.